From this set of data, you can see that the y value is increasing as you increase the x value. But however, this isn't descriptive enough. We need to explain how it changes. For example, is y directly proportional to x, or maybe it's proportional to the square of x. And we should also be able to figure out from the shape of the graph as well. So here we've got y is directly proportional to x, but does this set of data match that function? Or is it just a linear increase which isn't necessarily directly proportional? Or is it a squared relationship, a quadratic one, like so? Or some other kind of polynomial. So we need to be able to look at the data and figure out what kind of relationship it is between y and x, not just as one increases, other increases. Got another set of data here. So here, as the x value increases, the y value is actually decreasing. So, but what kind of decrease is it? Is it a linear decrease? You can see here with a negative gradient, or is it inverse proportional, or is it inverse square? It could even be an exponential decrease. We're not going to look at exponential decrease in this video, but we will look at it in the future. In this example, according to Bohr's law, the pressure and volume of a fixed mass of gas is inversely proportional at constant temperature. Determine if the data in the table supports this claim. Okay, we're testing if pressure and volume are inversely proportional, which can be written like so. Okay, and you can turn that into an equation by putting an equal sign and a constant like k. Okay, so I'm going to rearrange this to make P times V equal to some constant. So I'm going to test the data. If I do pressure times volume for any set of data, it should equal a constant across all sets of data. So let's do the first example. So 150 times 3.5, and that gives us 525. And let's test for another set of data. Okay, and another set of data. And as you can see, these numbers are fairly constant, so we can be pretty sure that it does follow the inverse proportionality law here, and that we can be confident that the temperature is probably constant and the fixed mass is also constant. So we need to write a conclusion once we've done this, and you need to do at least 3 sets of data to come to this conclusion. So we can say that constant k is constant or is similar or the same across the set of data as expected if it was inversely proportional. We can also do another way where we can try to look at the relationship between the data points. So for example, we go from 150 to 90. We've changed that by a factor of 6 over 10. Okay, so how I figured that out by doing 90 divided by 150. So if I go from volume of 3.5, I should become 10 over 6 if it's inverse proportional. Okay, so like this is the inverse function there. And that is true for 3.5 to 5.8. If I do 5.8 divided by 3.5, I'd get 10 over 6. Let's test this for another set of data. So here I'm going from 120 to 60, so I'm halving. So that means my data for the volume should double. And that is what happens going from 4.4 to 8.8. Okay, another set of data. So you need to do at least 3 sets of data. So here we're taking a third. So that should correspond to the other set of data here, timesing by 3. Okay, so we can conclude it is inverse proportional. The second example here. So we've got force and extension, and basically the question is asking us to check if it's directly proportional. Now, a common mistake that students make is they check the data and they can notice that they may spot that it's increasing by the constant amount. And that's what you'd expect if it was linear. So you'd expect that with direct proportional relationship as well. But just because it does that doesn't mean it's direct proportional. We need to check the equation. Okay, so we need to check. Let's write direct proportional as force is direct proportional to extension like so. Turn that into an equation, putting a constant there. So K should equal a constant. So force over extension, which I've written as delta L, should equal a constant. So let's try that for at least 3 sets of data. So if I do 0.1 over 5, I get 0.02. Let's do another set of data, 0.2 now. So I'm taking a range of data points. And as you can see, it's changing. Okay, so this means it's not following inverse square law. The K should be a constant, but it's not. So that means for some reason this force and extension is not direct proportional. A third example here, we're trying to test if this data here, the count rate and distance, follow the inverse square law. Okay, so is count rate inversely proportional to the square of the distance? So that can be written like so. Okay, so count rate is c here and the distance is d, and you can see it's inversely proportional 1 over, and it's the square there of the distance. I can turn this into an equation by putting an equal and a constant at the top there. And I'm going to rearrange this. I'm going to make k the subject. So that k, so if I do count rate times distance squared, I should get a constant. So let's take out a set of data, at least 3 sets of data, and check if this is true. So I'm going to do 74 times 1.5 squared, and that gives me 167. And if I do this for another set of data, let's do this point over here. So I'm taking nice easy points to measure. Okay, and I get 168. Don't forget to do the square as well this time. Okay, and if I do it now, final point here, I also get 168. Okay, so here I've taken points, not just the data points, I've also taken points from the line of best fit, okay, because you want to take the line of best fit because otherwise you're not really averaging over the data. So K is a constant, so we can conclude that it does follow the inverse square law. So you need to make sure you write a final conclusion.